In this video, I'm going to talk about feedback and conditional statements in Grasshopper. Specifically, I'm talking about three different types of feedback within the idea of a tool. The tool notifying, the tool refusing to do certain things, and the tool highlighting certain aspects. And I'm connecting those to conditional statements within Grasshopper, which is a way to, when you have analyzed data, to then sort that, process it, make different types of decisions on what you do or what you show to the user. A conditional statement in programming is called if-then, and if you've done any processing of Python, it's kind of a core dynamic of how you set up the logic of your program. Within Grasshopper, it's also kind of a basic element, but it's very worthwhile going over and emphasizing because it provides one of the basic building blocks. And conditionals and if statements really transform Grasshopper from being a kind of a form maker into a tool that lets you enact those rules. So what I'm going to show, and I'm going to show you a brief example before I start making this from scratch. It's kind of built around the spider stack example, but with some other constraints. I have kind of a setback law defined, and then my building is cut according to the setback law. So while I'm defining this volume, the building always, the form, the massing I've been created always kind of is confined within that setback. So that's kind of refusal in which the tool is only letting me do certain things, and in that way is providing me with a new result that I did not expect. There's also this kind of highlighting aspect where it's highlighting floors that are undersized and floors that are oversized, so that as a user I can say, okay, well I need to avoid those conditions. And it's also providing me with a notification component. It turns green if I fulfill an FAR requirement or a floor area requirement, and it turns red if the building is too small. You can imagine that this massing model could be used, for example, within a real estate constraint, where as a designer you have to create a series of floors with a series of programs with certain kind of formulas, and all these constraints of fitting within a given setback zoning law, fitting within a given total rentable square foot rule, fitting within a given floor. All these constraints are kind of exerted onto you, but this tool is one way to calculate those, present those to the user so that you can hopefully find exits outside of these constraints. And after this video, there's another video which involves kind of incorporation of all three things into a different tool involving using Python to drive some more logic. So for now, we'll kind of use this video to enhance or hone the idea of conditionals and feedback loops within your tool. So the first thing I'm going to do, in addition to using Rhino and Grasshopper, is to download a plugin called Human. Human is on the Food for Rhino website, and you can download it here. And when installed, it appears one of the tabs in Grasshopper. And the few things we're going to use, the one main thing is this render mesh to screen functionality that lets us use an interface. But more on that later. So once you have that, what I'm going to do is to create kind of a really quick iteration of that spider stack example. And some of this may be familiar to some of you, especially if you've done the previous tutorial, so I'm going to go a little bit fast. What I'm going to do is I'm going to create a layer that defines lot lines for me. And I'll create a layer that defines a mass, a positive mass. And so I'll just change the layer colors, something. And for now, I'm going to say, whoops, I'm going to create a series of points that define a lot line, and perhaps another series of points that define a massing. So in Grasshopper, especially if you've been following around with the previous tutorial, this should not be new to you. I'm going to use the geometry pipeline to grab some points on the lot line, and I'll use this tool in the mesh component called convex hull. Essentially what it does is it creates the biggest possible convex polygon that kind of surrounds all this. You can imagine it as if you took shrink wrap or some sort of thing and kind of shrink wrapped it around all these points. What form would you get? And it looks like this formation. Now, if one of these points are off, in the z direction, you notice that there's two different lines. That's because the convex hull returns multiple different outputs. This one is on the base plane, and this one is in the world space, which is to say the world space in 3 dimensions, and on the base plane kind of conforming to a flat xy plane. In this case, we just want the hull on a flat plane. So we'll get this one. So you see this bottom line is being highlighted, and let's just put this into a custom preview for now. And let's make it hot pink so that we see it. And as is my usual practice, I'm going to hide everything but the line. What I'm also going to do is I'm going to create some circles around these points with a given radius. Oops, spheres, excuse me. With a given radius. Perhaps not so big. And I'll also include these in, so that now I have these kind of interface. So now I've created my lot line. I'm going to do the same thing or a similar thing as my massing points. I'm going to use a 3D convex hull that I used in the spider sack tutorial. And now I've created this volume. I'm going to get the mesh edges just to highlight so that I can get a better 3-dimensional sense of what this looks like. And I'm going to preview everything. So I'm going to preview all these edges and maybe have the edges be white. I'm going to hide the geometry. I'll preview the mesh itself. And I'll give it a bluish color with some transparency so that I can see through it. So great. You can see I've created a solid volume and then a lot line. So one aspect that I want to talk about first is this idea of the tool refusing to do certain things. And that can I'll do that first because it doesn't involve specific Grasshopper conditionals. By refusal, I mean the tool giving you something other than what you thought you were going to get. For this example, since I have a lot line and this geometry, I'm going to try to kind of trim the building in 3 dimensions so that the building doesn't exist outside of the lot line. One way to do that is I could kind of split the geometry, but Grasshopper isn't always that great at splitting. So instead what I'm going to do is I'm going to create a mesh, an extruded mesh of this lot line, and intersect the mesh and the geometry. So here's how that will go. So now this is, I'm going to use this button to only preview what I've highlighted. This is the lot line. So I'm going to extrude this in the z direction. And let's say, by a certain height, which is great. But the problem with using a slider is that, what happens if I make my geometry taller? Then I'll have to adjust the slider also. So instead of using a slider to extrude it to a given height, what I'm going to do is I'm going to grab our our points and automatically make it so that the lot line extrusion is always higher than our geometry. So we already have our massing points over here. I'm going to grab those massing points. So there are a few ways to do this. One way is to use a bounding box, which if you give it a bunch of points, and if you say I want to get a union box around all of the geometry I've given it, it will create a box, a 3-dimensional box that can surround all of the geometry that you've given it. So from then you can analyze the height of the box and then send it to the extrusion. Another way to do this is, since we have a bunch of points, we only need the height, not the xy location. So I'm going to deconstruct a point to its component parts. And so now if I look at the z, all I get are the z values. And in here it just so happens that the z values are sorted, but they might not necessarily be. So what I'm also going to do is I'm going to use sort list. Whoops, wrong one. Sort list. What that does is that sorts points into a given order from ascending to in ascending order, so smallest to largest. And I'm going to right click and click on reverse the list. And then I'm going to get the first item. And by default, this list item gets, by default, the 0th item in the list. So if I just plug it in, the 0th item, or item index 0, which is the first item in the list, is also going to be the largest item because we had a list in ascending order, flipped it around, got the first item. Essentially, we got the last item in the list. So that's our maximum z height. So I could actually just plug that into this vector value and delete these two guys. And so what happens is that as my massing points get larger, the extrusion gets larger too. Now the last thing I'm actually going to do is I'm going to have this extrusion box be slightly larger or taller because when I do the because the intersection between the lot line box and the massing oftentimes works when they're not exactly sharing an edge, this top edge here. So what I'm going to do is I'm going to take this height, the highest z value, and add an arbitrary number to it. It really doesn't matter what this number is. I'm just trying to make this top plane of the mass and this top plane of the extrusion surface not be completely exact. Now we have this extruded form. I'm going to cap the holes, and I'm going to kind of clean up by hiding everything for now. So now we have this extruded lot line geometry. And I'm going to then do a mesh intersection. But this cap geometry is not a mesh yet. I'm going to use simple mesh to turn this into a mesh. Simple mesh essentially just creates the most simplest mesh possible from a BREP. In this case, because I have pretty simple geometry, right? I have a polyline extruded, I can use this. So I'm going to get the intersection of this mesh and our initial masked geometry, which is over here. And as a result, I have this geometry. So I'm going to do the same thing I did, which is to grab the edges and represent it. So great, now you can not see what's going on whatsoever. So there's a lot of stuff going on here. There's the lot line, there's the kind of mass itself, and then there's the kind of resulting intersection. Even if I hide everything over here, I still can't quite see what's going on. So I'm going to do my kind of split view mode, and I'm going to create two different named views. And again, this is from the spider stack example. Should be pretty familiar. I'm just going to call the second one design and the first one model for the sake of brevity. And I'm going to use a sync flounder camera, the one with the equal sign. And model. One shortcut, if you type a word between quotation marks, it automatically creates a panel with that word in the panel. And then design. I'm going to activate it with a toggle. And then I'm also going to use a timer component so that this thing runs around once every 20 milliseconds. So now you get these things synchronized. It's a little laggy, but that's because I'm also recording my screen for this tutorial. Now once I have these two viewports set up, I can kind of separate out kind of initial geometry from what the tool gives us. So I'm going to use a viewport filter and make the overlap, the intersection only show up in the design viewport. And I'm also correspondingly only going to make the entire massing show up in the model viewport. I'm going to make the lot line show up in both, that's okay, but I don't want the spheres to show up in the design viewport. So I'm actually going to separate out the geometry and the spheres and show the spheres in the model viewport. Again, the spheres are really our kind of UI handles, so to speak. And great. Oh, and I forgot to do this earlier, but I'm also going to create spheres for our mesh hull, or volume. So I have, and then looks like I just need to hide this intersection object. So as a rule, I'm just hiding everything but preview objects. And finally, I'm going to change this color so that's kind of, maybe more meaningful, or at least I have a separation between what's going on the left and what's going on the right. And I'll change some of the other colors just so that the output is different from the input. So this is great. So this is my input is different from my output. I've used a lot line to kind of carve away at my massing. As I move my kind of external massing around, it gets shaved away by the lot line. So that's like a certain kind of refusal in some way. And a refusal could be that the tool just doesn't do something. It could be that the tool does a calculation and perhaps automatically does something for you, or essentially has certain constraints within the design space that it fails to do. And because I'm not designing a building around the lot line, but it's just generating this form for me, I, as a user, am pitting my input against a complex or a certain degree of complexity that I did not foresee, and so can learn from that result. Kind of a valuable information coming from ideas or concepts that collide against complexities or processes. So that's kind of step one of feedback. This could, occur in a few ways. You can imagine, for example, a tool that redraws your line for you. When you give it a certain kind of polyline, it explicitly says, no, this is wrong, and recalculates and redraws a line for you. That would be a tool that kind of refuses in a certain way. So that's this kind of first idea of refusal. So really quickly, let's go on to notification. Notification I'm going to describe as when the tool tells you something via pop-up or vibration. And when I say tool, I mean like all tools in the world, not just Grasshopper. It's not just some sort of data is manipulated, digested for you, and turned into a yes/no kind of a binary on or off, look at me, don't look at me kind of information. And the point of the notification is not that it's giving you a stream of numbers, it's telling you based on a series of rules, and the tool incorporates a certain kind of intelligence within it. So I'm going to use the human plugin and this aspect called render mesh to screen, which is a very exciting and powerful tool. Essentially what it does is it lets you show something on the screen on the viewport as if the viewport itself was a 2D plane. And I'll kind of do this so that it's more easily understandable. So I'm going to grab the mesh of our intersection, our resulting geometry, and show you a quick example. So I've created the mesh, and I'm going to put it in here. The M inherits the mesh. The L inherits the location and pixel coordinates. Now I'm going to use this thing called the MD slider. It's a two-dimensional slider, and the output is from 0 to 1, but it gives you a kind of three-dimensional or an XYZ coordinate point. So by multiplying this output by 100, what I'll get is a series of values from 0 to 100. So you can see there's a three-dimensional point being created. The reason why I'm creating this is so that I can plug this input, this point location into a mesh to screen, and kind of easily can move this around. So you can see on the upper left-hand side corner of the viewport, you can see this mesh being moved. That's all we want. I'm going to hide everything else. Another thing, I can scale the size of this object. I can change a color, set a color, change the color. I can control the depth, so I can, if I have multiple meshes, I can control how high or low or how much they overlap or not. And lastly, I can add a toggle. So you notice that if I orbit, this also orbits above. If I set it to true, it's flat and remains static. So one thing I can do is I can also do text to screen with a kind of similar settings. I can say hello world, plug that test in here. You can see I've received the text as output. You could say something like floor area compliant, which is a terribly dry constraint, dry and necessary. And I can move that around a little bit. So now I have the setting where I've located this text in my viewport. Now the one thing I have to do is then to kind of use this, if this is a notification, to change the text or change the color based on what I'm doing in this masking model. So let's do what I did in the spider sack example, which is to quickly create floor plates out of this. So I'm going to create a series of mesh contours. This is our mesh. The start point is, yes, for the time being at 0, 0. We want to go in the z direction, and we want to say split by certain height. So our floor heights is 10 units, whichever that means in this Rhino world right now. In fact, I'll switch the units to feet really quickly. So great. So now we're talking about 10-foot building. I'm going to scale everything a little bit. Maybe our floor to ceiling distance is 15 feet. It's a little bit more luxurious, I'd say. Okay, great. So now I have these 15 foot floor plates. And I have these contours. Let's say I extrude them. I'll extrude them in the z direction to create a massive 1 foot thick floor slabs, 1.3 foot thick floor slabs. And I'll cap these surfaces. But the important thing is that I get the area of these things. And I'm going to hide everything I do and actually preview only the capped geometry and open this. So great. I'm also going to go back and change this color from green to something else because it makes me feel like I've highlighted the Rhino geometry. Maybe an orange. Great, perfect. So then I'm going to go and hide my area. So now I've created this floor plates, and I also have the area of all these floor plates. And I'm going to add all the areas together and flatten it so that I'm adding it across all the branches instead of within the branches. Our building looks like it's pretty cantilevered, but that's kind of fun. So now I have this area, and the question is, again, how do I use logic, or how do I kind of filter based on how do I change text or change colors based on what this number is? If you're used to programming, there's a few ways to do this, and if you're used to programming, you'll probably understand the if loop. But I'll just go on the process of evaluating numbers start to finish. So what we've done is we've done this kind of analysis here, right? And so I'm going to take an evaluation component. What this does is it takes an expression, and the expression is, say, x is larger than y, in this case. Or even to make matters simple, let's say x is larger than 5. And so if I plug that into our expression, and plug 5 into x, and I see what our result is, if x is larger than 5, it's true. If x is smaller than 5, it's false. That's pretty simple. If I add a y, let's say, and I can change this evaluation to say, oh, if x is larger than y, it's true. But since 4 is not larger than 8, it's false. If we reduce y, it turns into true. And one last note about this interface, you have to zoom in and you'll see these plus and minuses. If you click on plus, you'll keep on adding variables. If you click on minus, you'll delete them. So what we want to do is we want to say if the input is, say, larger than a certain number, give it a certain color, right? I can also change the name and say value. I can also say area. I could say, well, if, you know, if the area is larger than min floor area, and I'll call this min floor area. And let's say our min floor area is 15,000 square feet. And if we plug our total area in, you'll see that, yes, 17,000 square foot is larger than the min floor area, so we'll get true. And if we up that min floor area, we'll get false. So once we have this true-false value, which is called a Boolean value, because Boolean was this logician who defined a system of logic based on discrete true and false values. Well, specifically his name was George Boole. His name was not Boolean. So true and false values, then depending on whether this is true or false, we want to say color this based on two different colors. There are a few ways to do this. One is, actually before I go in, one thing to know is that true and false values are also numbers. And Grasshopper has this very convenient thing, that if I plug data into a data type, above here you can see that there's different types of data. Boolean, integer, number, text. If I have a Boolean value and I plug this value into Boolean, you know, I'll say true and false, yes. But if I try to plug this value into an integer, Grasshopper tries its best to convert it actually into an integer. So it gives me 1 for true and 0 for false. Now, sometimes this doesn't always work. For example, if you have a point and you plug this value into the point, you'll see that I have an error because it has no idea how to convert a true-false value into a point, or how to convert a number into a point. You could do things like, if you have text, you can convert it into text, in which you're getting the text false with F-A-L-S-E, those characters strung together. So one thing we can do is, there are a few different options, and I'll go through the easiest one, which is to convert it into an integer, and so our value is going to be between 0 and 1. And I can use the list item component to essentially plug this into which item I'm getting. So based on whether this is true or false, I'm going to get the first or second value, or the 0 item with index 0, item with index 1. I'm going to use the merge component then to say choose between two different colors. So I'll use the merge component to put these two different colors into a list in a given order. So you'll see that, you know, as I change this red, this one changes over here. And so if I plug this into the list and input for the list item, since it's getting the 0th item, it's getting 92, 141, 237 as its output. And if this starts being true, it returns a 1, thus it's getting the second color. And so then what I can do is I can then plug this into, as a, since this is a color, I can plug this into our preview component. So instead of these two swatches, I can kind of connect this into here. And actually, before I could do this, right? One other small trick I'll show you is if you hold down Shift and Control, you can actually grab these the wires from the output and plug them into someone else's output. So you can see that this color has changed. I'm going to make these a little bit clearer. Actually, the second item is means true, and the first item means false. I'll say red for true and blue for false. Oh, sorry, red for false and blue for true. So now this means that since our area is, yes, larger than the minimum floor area, we get a blue result. But if we kind of push up our desired minimum floor area, we'll get kind of a red result, or a red notification. I could do the same thing for text also. So instead of floor area compliant, floor area, I'll be able to choose between two different types of texts. Use the same item component. You can see the text that comes out has changed as a result. And I'm going to plug this into the text-to-string component. And it looks like I've switched the left-hand side, the error and success messages. I'm going to switch them over here. So you can see that the floor area is too small, but if our threshold for what an ideal floor area is, then all of a sudden it turns to floor area compliant. So I could do something like, okay, well the floor area is too small, so, oh great, now it's compliant all of a sudden, but when I start shrinking the mass downwards, say, so compliant, all of a sudden it's too small. So this is one way in which there's a notification, like a binary yes/no. I've calculated in some basic intelligence of, do I have enough floor area? And the notification is a binary yes/no that embodies that certain type of calculation. Let's go on to more kind of interesting things, and I'll also talk a little bit more about different ways to do this kind of sorting. Before I go on, I'm going to kind of arrange and clean this up a little bit. And that's kind of a really important aspect in Grasshopper, because if you start moving around things too much, it gets very messy, and later you can't read your own code. Because Grasshopper is graphical, this means that there's a great amount of kind of spatial composition you have to do. If you select a lot of things, these buttons can make everything align, or you can space them out equally. But I personally find that it's more helpful to kind of move things around by hand. So I'm going to delete some of the panels that were telling me what my output was. So this is for the message. This is the yes and no for the colors. I only need one slider, so I'll share that slider and delete that button. Delete that. The evaluation happens right here. Delete the Boolean. So I can kind of, this only deals with the interface. And one good kind of process is to kind of group a lot of things together. This is done by hitting, selecting and hitting Control-G, or selecting and, let me undo that, or selecting and middle clicking and clicking on this little group formation. You can double click on the group to change how the groups are formed. You can right click again and say, floor area notification. And you can also change the color of the group from purple to something else. Let's see. And if you drag the group, you can move everything around together. This can be very convenient to kind of understand what's going on here. So that was kind of a basic conditional, just doing a yes, no with an evaluation and doing an integer. But let's say I want to do something a little bit more complex, just a slightly bit more. And I want to take all these areas and I want to color each floor area. Now I already did that in SpiderStack, so I'm just going to do that really quickly. Actually, in SpiderStack, if you recall, what I did was I scaled this area to a 0 to 1 value and I plugged that directly into the kind of color component. I'll do that again, but with a slight twist, and then I'll do a kind of another approach, which is more kind of logic oriented. So one thing I can do is I can take all these numbers, use the bounds component, grab all the areas, flatten them, so that I get the bounds, the highest and lowest bounds of the input numbers, and so that accurately translates all these numbers from 0 to 1, which is great. I can use the gradient component, and what this does is, given a lower limit and upper limit, so 0 to 1, in this case are the default, you give it a parameter as going between these numbers, and it'll give you the corresponding color interpolating between these two color points as a gradient. So for example, if you have 0.5, it'll give you this color over here. If you give it the number 1, it'll give you this color over here. In this case, our lower limit and upper limits are already recalibrated based on this remap numbers function. So I just need to plug in these numbers, and I'll get a series of output colors. And then instead of coloring all these different surfaces based on one color, I can plug this guy in. So you can see I have a gradient, and I can right click and choose between different presets, and also move these around. I can drag a number out here, I can right click on it. So this is a way to kind of do a simple representation in terms of a color kind of map of my square footages of my floors. Let's make more floors. But oftentimes, this is not so helpful because I'm not explicitly doing any calculations. The problem with this kind of representation is, it's intuitive but not discrete. So when you look at this, you say, aha, I see the darker red is larger than the pink, but you don't know exactly by how much. So instead of doing this gradient-based calculation, instead I'm going to do a series of rules, make a series of rules. So let's say there's a constraint that I can't make floors that are too small, and I also don't want to make floors that are too big. So I want a kind of sweet spot, and I want to highlight which floors are too big and which floors are too small. So one way to do this is I could say, okay, I already did this larger than component down here, right? But in the evaluation function. But I could say, if the area is larger than, say, 1500, return true. So I have a series of true-false values. And I do the same thing. Okay, so and then I say, okay, but so if the area is smaller than 1,000, let me know. So then I have a few kind of constraints here. I have, if the area is smaller than 1,000, then I want it to be color A, let's say. If I want it to be both smaller than 1,000, not smaller than 1,000, and not larger than 1,000, then I want it to be color B. And if it's larger than 1,000, then I want it to be color C. So one Boolean logic way to do that is to say, well, I find it helpful to write this out. Smaller if smaller, color A. If larger, color B. if not smaller and not larger, color C. So one way to do this is to say, okay, if my floor plate area is larger than 1500 square feet, then give me a true or false value and convert it to an integer, and do the thing that we did earlier. But the problem with this is that what happens if you have many different types of logic you want to kind of combine together. So I'm going to use the evaluation function again. So what I'm going to do is I'm going to use the evaluation component. And I'm going to plug this into x, but instead of x I'll call it value. Instead of y I'll call it min. And I'll say our minimum is, let's say it's 5. And actually instead of value I'm just going to plug another slider in just to show you how the operation goes. So I'm going to create a panel that says, okay, if val is larger than min. This is exactly what we did before, but bear with me for a moment. The other thing is that values like min are actually mean other things within this kind of scripting kind of syntax, so I couldn't just use min, so I'll change it to min val. So you see that if value is larger than min val, it's true. If value is smaller than min val, it's false. That's great. This is val, and this is min val. Now I can also use the syntax. I can wrap this thing in an if statement. So if open parenthesis value is larger than min val, and can write my own syntax. Yes. And so if this is if this statement in value is true, it returns the first thing. If not, it returns the second thing. So you can see I get these different. If val is larger than min val, I get a yes. Now the reason why this is good is instead of yes, I can actually nest and add another if statement. So I'm actually going to add max val here. I'm going to say actually our min val I want to be 3. My max val I want to be, let's say, 7. So I can write a statement that says, okay, if the value is larger than min val, then do something here, evaluate a statement, and the evaluation statement is saying, okay, if value is smaller than max val, then we say, great, we're in the sweet spot. And if not, we're not in the sweet spot, we're actually larger than the max val. So we say too large, and I close it again. So what I've done is, if you read this out loud, I've nested one if statement inside of another. So if this is true, it evaluates this one, and if this value of this statement is true, then it returns this sweet spot string. If this internal expression is false, it returns this too large string, and if value is smaller or equal to min val, it returns too small. So what that means is that now I can say, okay, if value is too large, larger than 7, it says too large. If it's in the middle, it says sweet spot. If it's smaller, it says too small. You can add, multiple more of these and kind of continue to nest this if statement if you want. This is one way of doing getting this. And instead of sweet spot too large, too small, I can do the same tactic, which is to say, okay, I'll say sweet spot is index 1, too large is index 2, and too small is index 0. And the reason why I'm doing that is because so that I can make a list of 3 values, and if the value is too small, it gets back the 0th number in the list. If it's in the sweet spot, it returns the first value in the list, or the second value in the list at index 1. And if it's too large, then it gets the third value in the list at index 2, because lists start at index 0. So what I can then do, I'm going to delete this, is I can do my kind of color strategy where I say, okay, too small is red, sweet spot is like a nice shade of maybe a very, very light green, and too big is a shade of kind of fuchsia purple. And if I merge these items into a list in corresponding order, then I also get the order, them ordered properly into a list. I can use the list item component to say, okay, from this list, grab this index, and then it'll return to me the correct value. So depending on where the slider is, it gives me the right color. Now instead of these sliders, I'm going to plug the value from the areas in, and instead of this min value being 2, which is obviously way too small, I'm going to talk more about maybe the minimum value being 1,000 square feet, the maximum value being, I don't know, 7,000 square feet. And these colors I'm going to use then color my floor slabs. So instead of a singular swatch, if I plug these colors in here, you can see that these floors are lower than my minimum value threshold and have turned red. If my minimum value threshold goes up, slowly, all these floors are not adequate. And if our maximum value threshold goes down, then it's saying, okay, these floors are too big. Let's say for some reason that's our requirement. So then, the user is notified, the user's, the tool is highlighting certain parts of the building, and the user has to design something based on that. So, now there's this game of, okay, don't have any red or purple elements, which means perhaps, adding more points above. This is a kind of highlighting that's very kind of logic dependent. And you could even imagine that, actually what you want to do is you want to engage in a certain kind of refusal. If it's not sufficient, then you don't want to actually even show the parts that don't work. So maybe you could do this a few ways, right? You could have it fuchsia be entirely transparent. So it's almost like parts of the building disappears. And you could say, okay, these white lines, they're actually not kind of hide that aspect. So that what appears here is like only the building that really matters. You can even say that the floor plates you're using, you want to kind of create kind of new geometry, only the floor plates that are manageable. So you could conceivably get kind of the outer points of the floor plate massed together in a new 3D convex hull, and create a new kind of form. But in this way, the tool is engaging in a certain kind of refusal for me. It's refusing to show certain parts of the building because it's saying, no, you can't do that, or that's not valid. Let's see if I can try to get. Okay, so all of a sudden, we get this form. Only parts of the building really make sense. Okay, this is a little more ideal. We start moving the building a little bit and moving these points. So now all of a sudden I've made a building that makes sense to an extent. And again, this is like one way I've kind of gamified or made playing with the tool a little bit fun to find exits out of constraints and compliant with the floor area, whatever that was. And I've also kind of excised certain parts of my building that don't fit certain requirements. Now the other way I'm going to show you how to do this kind of sorting based on a logic is using the dispatch function. So I'm going to use a larger than component and have a number 1500, and this is kind of another basic building block. Essentially, if you have a list of true-false components, instead of using the integer component and converting it into 0 and 1s, we're going to use the dispatch component. This is essentially works as a filter. What it does is, given a list, so let's say the capped geometry, and a pattern, a true-false pattern, it sorts the list into two parts, those that returned true and those that returned false. And I can kind of see this by plugging this into a geometry component. can see that this is all the floor plates that had an area larger than 1500. This is all the floor plates that had an area smaller than 1500. So I could do something like, let's see. Let me just show you a good example. So these are all the areas larger than 1500. These are all the areas smaller than 1500. So this is all the areas that are too small. And I could do also from this kind of another pass. I could say, okay, I want the area to be smaller than 2500 square feet. So out of this, I get a series of another true-false values. And I can actually use the dispatch command again, but on our larger than our minimum value components, and using this pattern. And if I look at the geometry, this gives us all the numbers that are compliant, all the floor plates that are compliant. This gives us all the floor plates that are too big. So this is too big. This is just right. Just right, too big, too small. The reason why we can use the dispatch component again on this is that you'll notice that if you plug our input in, we have this tree structure. This 0:15 means that on branch 0, sub-branch 15 lies this item. And if we pass it through one process of dispatch, it maintains the structure. So it's saying, okay, the branch structure is still the same, it's just that under this branch there's nothing there. So if we pass our area through this logic component that gives us a series of true-false values according to that's structured like this branch, and since the data structure is the same, if I plug the output of this logic into a new dispatch function that receives a result of this dispatch function or component, because I've maintained the structure, I can also kind of filter correctly what's just right or what's just too big. So too small, just right, too big. And then I can have 3 different preview functions with 3 different colors to say, okay, this is too small, this is just right, this is too big. I can go ahead and hide everything else. And I've done the same kind of filtering using dispatch. And you can see my approach is a little different. Previously with the evaluation, I've selected 3 different types of colors, selected from 3 different types of colors to match the order of the floor plates. In this case, I've actually kind of isolated the different kinds of geometry and just colored them using the dispatch function. The dispatch function, I would say, is one of the main building blocks of Grasshopper logic, doing kind of if-then statements like this. And to go back to the tool, the process behind the tool, what this logic is doing is to highlight certain aspects of what I'm looking at, right? So I've created the lot line that does something, cuts off certain areas and just refuses to show some parts. I'm using a notification to show me something about what I'm doing based on a certain yes-no logic. And I'm using the highlight function to highlight certain aspects. In this case, I'm actually going to make it highlight, which is to say, I'm going to have it only show the parts that work. And so this kind of feedback tells me things that I didn't know or didn't quite anticipate. It would be very painful to kind of go and model this masking by hand, but instead I'm creating an initial series of inputs, and the tool is processing something and then telling me a lot of things. Yes or no, it works, but only these floor plates are really viable because these are too small and these are too big. And on top of that, it's refusing to show me certain parts that go outside of my lot line. One last fun thing is I can previously the lot line was kind of straight up extrusion, and I can kind of pretend that the lot line is actually like a setback line. So I can try to implement that really quickly before I go over to the next example. So I have this initial line and extruded, but say instead of that extrusion directly, let's say there's a rule in which the setback is 150 square feet. It starts from 100 square feet and kind of slopes back at an angle of, say, 123 or 2260. I'm not going to deal with the location of the street and all that. I'm just going to pretend that from the lot line you can go straight up for 150 feet, at which point you have to angle to a 10 to 30 or 1 to 3 ratio. So how do I implement that? So I have this lot line. Let's say I have to go up 150 square feet. So that's our kind of base height at which we can keep on going up. And then after this we have to start kind of sloping or narrowing our maximum envelope. So what I'm going to do is I'm also going to, after that extrusion, instead of the extrusion, I'm going to grab this geometry and move it upwards 150 feet. And then I'm going to figure out how much higher I have to move it to. So this is the number, move it up. And I'm going to subtract 150 from this number to give me 12 feet. So I have to move this line up 12 feet more. I have to move the moved line up for 12 feet. If this line goes up, right, the line has to go higher. Now, that's all good, but I actually want the sides of the lines to go in, because remember we have to have that setback rule of 1, 2, 3. So really quickly, I'm going to figure out the angle of 1 to 3 ratio. 1 to 3. This is a triangle where this side is length 1, this side is length 3. And this would be the arctangent of a third, I believe. Excuse me, this angle would be the arctangent of 3. But we could also, since we're in Rhino, we can measure the angle. I'd say the first line, I'll explode this. Here's our first line, here's our second line. And so that's 71.57 degrees. But, you know, actually we don't quite need this. All we know is that for every rise in 3 feet of height, this line has to go in 1 foot. So if this kind of excess rise above 150 feet is 93, if we divide this by 3, we know that after that the lot line has to shrink by 31 feet. So I'm going to do an offset on this curve. I'm going to turn it into a negative number so the offset goes inwards. And I'm going to offset this curve by this distance on the xy plane. Now this broke, and the reason why this broke is because I'm trying to offset too much. Let's figure out a way to fix that in a moment. But for the time being, I'm going to go back to model viewport. And I'm actually going to disable my viewport, my human viewport, because I think it's right now making my computer a little slow. So if I use that negative value and do an offset on a curve, our curve gets broken because it's too small. So that's because this curve in the middle, and let me actually turn on the view preview. This curve in the middle converges to a point via the setback rule before these lines are broken. And that's a little bit of a problem. One way to solve that is, instead of grabbing the line, figuring out how high we have to go, and then making a setback based on that, I could actually instead do the other way around, in that I grab the kind of area of the line, and I'll grab the shortest point from, I'll grab the centroid of this polyline boundary. I'll grab the centroid, the shortest distance from the centroid distance to the points. So I'll get the control points of this. I'll get the distances from the centroid to the points. I'll sort by an order. And then I'll get the smallest distance. I'll say which is approximately 26. So what that means is that this point could shrink by 26 before this line pretty much disappears, or this polyline is non-existent, or it doesn't work with the offset tool. Or in other words, if I show our kind of setback diagram again, because our ratio of our setback line is 1 to 3, or 1 run to 3 rise, since this is the maximum run possible, I can also multiply this number by 3 to figure out our maximum point of our kind of lot line envelope, which is 78 feet. So at 78 feet, this lot line kind of tapers to a single point. So what I'm going to do then is, it's a little trick. I'm going to make a tiny rectangle, at that point, which is, say, at the centroid, on the xy dimensions of the centroid. So I'm going to deconstruct this value into x and y, and then I'm going to recompose it back into a point. So I'll use the x and y values of this point, but the z values of this guy, this is 78. The z value, mind you, has to be added to 150, because 150 is, our calculations around here are dealing with 150 feet above the ground. So add 150 to the z value, and this value is over here. And I'm going to clean this up in a second. So plug the z value in, means that this is the topmost point. And because what I want to do is I want to create a lofted envelope and then do an intersection, I'm going to create a very tiny rectangle up here. The reason why I'm doing that is because you can't loft points to a surface. So by creating a very tiny rectangle of 0.5 by 0.5, it's pretty almost the same thing as creating having this taper to a point. So then I'm going to take all these 3 lines, the topmost line, the middlemost line over here, and the bottommost line. And I'm going to loft these 3 lines together. Looks like perhaps this rectangle got ignored in the process. Aha, I see. Okay. I had to flatten this rectangle. And I'll set the loft options, because I don't want this kind of bulbous form. I want all the surfaces to be straight. So it's a closed loft. That's false. And I want the loft type to be straight. So plug 3 into this. That's more like it. This is the condition I want. I'm going to cap the loft. And so this is essentially our lot line envelope. Depending on our ratio from rise to run, which is this guy, you can see that the ratio changes. But I'll plug this in to what we were using before to do the intersection. And I'll grab everything, move it upwards to kind of clarify later. And you can see that when I do that, the intersection mesh becomes this one. The resulting volume becomes this thing. I then slice it up. I am going to hide everything over here. And analyze a little bit what we're dealing with. Looks like this capping failed. That's okay. One thing, instead of extruding a contour and capping it, I'm going to make these into surfaces and then extrude them. Then these extruded forms, I'm going to enable this thing. So now whatever geometry I'm using is corresponding to the setback rule. And you can see that if my lot line was larger, then the total height of my building changes as a result. Let me move these 2 points to make that more clear. The total height of the building became taller. Finally, as for simplifying this process, just a little complicated. There are a few ways to do this. You know, here, if you remember, I cheated by having a rectangle at the top instead of lofting it to a point. I could fix that. Alternately, I can do this thing called clustering, which is a little bit more of an advanced technique that I will explain later. But I can grab everything. I'm just going to grab everything, group it, and call it setback envelope as a way to explain the process that we were doing. So that's kind of all in one example. And if I turn on the interface again, this is an all-in-one example of something that has a notification, highlights certain aspects, engages in a certain kind of refusal, and actively doesn't show me certain things in order to compute for me or to create a kind of a design space, design a design space from the user, and thus create a tool that maybe feels more like playing because you're guaranteed to work within these given constraints that you've set up for yourself. The next video is going to be a little bit more play In this example, I'm going to talk about tools and feedback, and I'm going to use Python and clustering. I'm going to introduce kind of a basic usage of both of those techniques within the tool. I'm using an example that involves a given lot line that is drawn and a given FAR, and given those two constraints, the technique or the process of the tool is to kind of push these objects that are actually negative spaces into the space of the building, and this tool enables the user to continue to carve out voids, but if you notice on the right, the height of the building changes in order to maintain the total FAR. So this is one way to say to adhere to a given constraint while creating an interface that has the feeling of creating these negative space objects, crafting them, pushing them into the building. So I'm going to get started ahead with creating this from scratch. So I'm going to do a few things. I'm going to start with a layer that has a bunch of points on it called lot line points, and a layer for negative masses. I'll create some B-reps, and I'm going to jump in really quickly and use a geometry pipeline to get a bunch of points. Use the convex hull on the XY plane together to grab the geometry on the ground XY plane that is a lot line. I'll use the preview line weights component actually to show that geometry with a specific swatch color. And the reason I'm using the preview line weights is it's able to show the line weights in Rhino with a given thickness, or show lines with a given thickness, which is helpful if my lot line is important to me, which in this case it is. I'm also going to use the same geometry pipeline component to grab B-reps instead of points. That's my geometry, and this is neg masses, and this is actually my lot line. I'm going to group it just so that I have like a visual highlight of what's important to me. The other thing I'm going to do is I am going to add variables for my maximum FAR or the floor height. Let's say it's 13 feet. Great. Now I'm going to go and hide everything that's not relevant. And I'm going to show you what I'm trying to do a little bit in Grasshopper first before I jump into working with this in Python. So like the example I showed, what essentially I want to do is I want to kind of have the maximum lot line form with the maximum FAR. So that would be the maximum FAR times the floor height. That would be our actual height of the building, or the massing, extruded in the Z direction. So this would actually be what our kind of maximum envelope would be. And I'm going to cap it and do a solid difference with that and some geometry. Let's say the negative masses in this case. And that comes out as some sort of geometry that probably doesn't look like much, since none of the masses are actually intersecting with our kind of maximum envelope. But you can see that as I start to bring it in, I'm going to hide all the geometry actually, and hide everything here. You can see that it's carved away as we want. Of course, when this is carved away, this massing has lost the floor area, and if one way of calculating FAR means that this massing can also go up correspondingly. The question is then, how much should this building go up? That's actually a pretty hard question to calculate, because if the contour of the building is changing as you go up, then it's unclear at which point you should stop. This problem is the same problem of essentially having a vase of sorts. You can imagine if this was an open vase with an open container and you had a given amount of volume, the question is, if you poured a given amount of water in this volume, what would the water level be when all that water was poured in. That's actually a pretty hard question to solve computationally, or solve algorithmically rather, to solve with a rule, because this cutout is relatively simple, but if we start having a slightly more complicated geometry, say like a sphere, and one side of this vase or this building is carved away, then you can imagine that as you pour in water, more water has to enter in order for this kind of water level to rise. But in the middle, the water level rises faster because the cross section is smaller. Now, of course, when I say we use this metaphor of water, what I'm really talking about is volume, or the total kind of cube footage of this building, which divided by the floor area is the FAR. So the FAR problem and the how much water can you pour into an irregular shaped vase and how do you know where the water level will be problem are essentially the same in both hard. So we're not actually going to solve it mathematically, but we're going to solve it computationally. And for that we need Python. We also need Python for another reason, which is, let's say we start really squeezing in buildings in here. Then you can imagine that this building height actually goes up higher a lot more. And if it does, and if we place the object up here, you would imagine that this increased building height would also have to carve out itself from that object above what is usually the kind of what would normally be outside of the bounds of the initial envelope. So it's kind of a little tricky question, but Python can solve this to the rescue. So the thing I'm going to do is I'm actually going to, just to describe to you what I'm going to do in Python, I'm going to take this volume and actually multiply it by, make it twice as tall. An envelope that's twice as tall, and we'll cap it and do the booleaning in, and we'll get this kind of resulting geometry. And then I'm going to try to find out, okay, given our max FAR, our floor height, and our kind of lot line area, we have a certain amount of volume of space, and what is the level at which that line stops? That's the question. And so the way I'm going to do that is I'm going to first of all draw a line at our original height, so our max FAR times our floor height. And I'll draw a line and I'll split this BREP into two. And I'm actually going to do that right now just to illustrate what exactly I'm doing, because it's important to understand the theory of what I'm doing. So let's say this was the given height. So I'll split the BREP according to the given height. I'll take the bottom half and I'll say, okay, what's the volume? And then I'll calculate the FAR of this massing, and I'll say, okay, how much more FAR do we need? In this case, let's say that this building or this massing has an FAR of 7 when we really wanted 10. So the program would say, okay, well, we need 3 more FAR here. And then it'll actually increase the height, not to 3, but half of 3, so say 1.5 FAR, add 1.5 FAR more. And then I'll try to calculate again what exactly this new height is. So it could be that, this building gets raised again, and this is computed again. And so the next time it could say, okay, it's actually, this massing is 8.5 FAR, so there's 1.5 FAR needed. So then it tries to add half of that 1.5 upwards. And the reason I'm adding half is that that's kind of a surefire way for these calculations to converge on a stable number, so that each time when it's calculating, it's only adding half the amount it needs, or maybe 3/4 of the amount it needs in order to fulfill its FAR. And if you do this enough times, eventually it'll start to converge on a height that is very, very, very close to the max FAR. Now we could technically do that in Grasshopper, but since I'm trying to, I want to show you how to use Python, and in Grasshopper it would be very messy, I'm going to use Python, which is very a joy to use, and a very, very powerful programming language in general. It's what's being used by scientists for statistical analysis. building web apps, building mobile apps, machine learning, you name it. So essentially, as I mentioned, what Python is going to do is it's going to grab this subtracted volume and then just slice at certain points. So what we need to give it as input is this object. But before that, I'm going to do a really quick introduction to Python. In the skills tree, there's another introduction to Python, but you should look at that. But the Python component is it's called GHPython, or the plugin is called GHPython. But if you type Python, this comes out. And if you've opened the C# and VB.NET components, it's kind of a similar thing. If you double-click on it, an editor opens. If you right-click on it, you can have it have external input from a file. You can read a file, plug it into the code parameter. You can add variables, delete variables. But for the time being, I'm just going to use I'm going to call this submass. I'm going to say max FAR, because we need to know what our max FAR is, and I'll say lot area. And our submass is going to be this geometry. Our max FAR is our max FAR, and our lot area is our lot area. Now the other thing to know in Python is that if you right-click on the inputs, you can have a hint. You can tell Python what these objects are. In this case, the submass is a brep. The max FAR is a number. I'll say a float. And a lot area is also a number, which is a float. Floats are numbers with decimal points. Ints are integers. So 1, 2, 3, 4, 5. Strings are text. Complex numbers, I suppose, are involve I, the square root of -1. But for this case, I'm just going to set the variables to be the correct types, and then I'm going to double-click and open this editor. Now, Python syntax, I won't go into too much detail, but if you do, Python doesn't have any semicolons. It uses whitespace as syntax. Again, uses look at the Python intro video if you want to go more into Python. But the two things that you should really know is these commands. And what this does in Python, import kind of invokes external libraries, libraries being kind of other code that other people have written to interface with other programs. And in Python, the import statement specifies what parts of that code to bring in. So in this case, I'm importing a part of a code library called RhinoScript syntax, and I'm calling it RS because RhinoScript syntax is kind of a pain to type. The same deal below. GHPythonlib.components, I'm renaming as GHComp. Now, what are these two things? RS includes all the stuff you can do in Rhino. So you can explode curves, you can get the color of objects, you can pull a curve, all of these are probably very familiar. And if you start typing rs dot, you'll start to see this drop down. The GHComp is actually also really exciting. It's in a recent version of Grasshopper Python. This actually exposes everything you can do in Grasshopper. So I have the ghow component installed, and in this case I can do ghcomp.ghow and run all the Grasshopper components in Python. This is very powerful. And most of the time, whenever you do anything in Python, these two lines are just kind of have to memorize. These are kind of standard and what you need in order to do anything in Python. The other thing, if I say print hello, and I press F5, which is test, you can see the results here. If I say A equals hello, and I click on OK, you can see that the output of A has turned into hello. If I do A equals max FAR times lot area, then you can see that it's just taken these numbers and multiplied. So Python automatically grabs all these variables and sets them within your editor, which is convenient. Now let's go into the details of what I'm actually going to do. So what I said was, given this initial mass and this submass, I'm going to, at a certain height, divide, split this BREP into two. The other thing I need, actually, that I realize, is not just the max FAR, I also need to know the floor height, because I need to know at what height I should be cutting things at. So I'm going to edit this, but our initial envelope height is our max FAR times our floor height. I'm going to ask it to print at that. So that's 260 feet, which sounds about right. So what I'm going to do is I'm going to, and this is good practice within Python, I'm going to search for the component that can do a kind of splitting. So here's split BREP, and if I do split BREP and do an open parenthesis, I can see what it needs. It needs a BREP and a cutter. The other thing I can do is look in Grasshopper components and try to see, here's also a split BREP, requires the same thing. I'm trying to see if there's possibly a splitting that can require an XY plane instead of another BREP. But let's just use rs.splitBREP. rs.splitBREP. And if I open the parentheses, you can see all the things it requires below. This is very helpful. The parameters means BREP ID, so the BREP, the cutter ID, and whether or not I should delete the input or not. So this is the BREP, which is submass. The cutter is, let's just call it cutter for now. And this is not going to work because when I run it, it says name cutter is not defined in line 8. That's right, we don't have a cutter. The cutter needs to be a plane, so we also need to then create a plane. In the RhinoScript syntax library, everything is done by add. So let's see. It looks like this can possibly do it, but I'm not actually sure what add cut plane is within RhinoScript syntax. One of the things to know in Python is that sometimes what's exposed to Python, what you can do in Rhino, are not always exactly the same. It's a little confusing. So add planar surface. So maybe I'll actually add a rectangle given a plane. In the plane, I need the xy plane, so I'll do rs.world xy plane. I need a width, let's just say 10 for now, and a height. And I'm going to put hash in front of line 9 that turns it into a comment. And looks like it didn't like that. Why is that? rs.add rectangle. Plane width height. It looks like, sorry for that delay, world xy plane is actually a function, so if I do this, it works. Now, what's going on here? If you've never touched Python before, or if you've done a little bit of Grasshopper, actually, I would suggest that you just go through the Python intro, because I'm not actually going to explain what functions are. But within the add rectangle method within the rs class, I'm invoking this thing called rs.world xy plane to get the xy plane of the world. and I've created a 10 by 20 rectangle, but I can't just add it, I have to set it to something. So if I do a equals rs.rectangle, it will show out as a polyline curve, and if I click on it, you can see that that's all the way down here, which is great. I'm going to say set it to 100 and 100, and then run it again with F5. And now you can see it's down here also. But I don't quite want this to be down here, I want it to be above. And so maybe I need to define a cutting plane. So I can do this thing called move plane, which moves a plane to an origin. So I'll say, okay, I want to move the world XY plane, and I want to move it to a cutting point. So now I have to define a cutting point. Cutting point. And I can define this a lot of ways, but I can also just define it as a list. So this is the syntax for a list. So I've defined a cutting point, I've just defined a cutting plane, I'm going to add a rectangle on that plane. So you can see that if I change the x value to 100, cutting plane moves up. Now in this case I can, instead of the z value being 100, I can change it to init envelope height. So now my cutting plane is in the right location, it's just not, the rectangle is just not shaped in the right place. One thing I could do, actually, is instead of a rectangle, I could add a circle and give it a center. So and a radius. I set that, even if I set A to be that, then I get a circle, which is great and convenient, and it's centered on that point. And now I'm also going to then create a planar surface from that circle. Perhaps it's add planar surface, yes. And instead of setting this to A, I'm actually going to grab all of this, cut it, and paste it inside here. So now A is actually a surface, which is perfect. We don't actually need, we're not using A, this is just a shorthand so we can see it. Let's just call this cutter. And so when I actually do the rs.split brep, and if I do print A, you can see, and this is a little hard to see, but you can see a system.uid object and then another object, and both of them are inside brackets, which means that they're in a list. This is might be a little confusing, but essentially what this means is that the length of A, there are two items in it, one's the bottom, one's the top. So if we say, okay, A equals split mass and the 0th one, this indicates get the 0th item of the list. Whoops. Then you can see A is set to the bottommost one. But we're not just going to set A to the bottommost one, we're going to actually cap it. So rs.cap planar holes. Let's see if that works. Returns true or false. So it looks like maybe this is what we want to do. So it looks like cap planar holes actually edits what's inside of the variable that's passed to it. So if you set, because if you do rs.cap planar holes, you can see that it returns true or false depending on whether it failed. So if we set to A to equal rs.cap planar holes, it'll just say true. That's not what we want. We don't actually want to set A to true or false. We just want to execute this function that edits what's inside of it and set A to that. So that's great. Okay, and I'm going to clean this up a little bit. Now, all this stuff could be cleaned up a little bit because, if you notice there are a lot of variables that I only use once. But sometimes it's more important to have readable code than efficient code. So the other thing I'm going to do is I'm going to type cutting at and then comma, so that comma kind of joins various objects to be printed out together. So you can see I'm cutting at 260 feet, and that's the lower mass, and I've capped it also. And what I'm going to do is also get the volume of it. So rs.volume. Volume may be actually hard to measure. In which case we'll use a grasshopper component. And let's see. It doesn't like that for some reason. Very unclear as to why that is the case. I'm actually going to try to go back in and look for a volume in this, because I'm pretty sure it exists. I don't quite remember. I think it's called surface volume. And I'll put our lower mass in it. See what I get. So you can see I get two numbers. What exactly does that mean? The first number is the volume, and the second number is the error bound. I'm not really interested in the error bound, so if you get the first number, that's our volume, which is great. And again, I could combine this onto a function, but I won't do that right now. And given our volume, if you divide the volume by the lot area and by the floor height, you get a max FAR. Which is interesting. Perhaps not what we were expecting. Oh, it is what we're expecting, of course, because our max FAR is 20. So it looks like our effective FAR is this. Is 10.4. Now, if you think about what this entire chunk did, and I'm going to, instead of saying init envelope height, I'll call it cutting height. Given a cutting height, it did this calculation. It split it, it capped it, it got the volume, and it printed out the effective FAR. And I'm actually going to put this inside one giant function. So I'm going to say function get effective FAR at height h. And then I'm going to highlight everything and hit tab. So everything here is now running inside of get effective FAR at height. And I'm going to put this at the start of my code. And so now if you imagine that this is a start, I've calculated the cutting height. I'll do get effective FAR at height. I'll put in the cutting height, and I'll print that. But I won't get anything yet. It also looks like I've misspelled something. Aha, here we go. Just going to copy and paste just in case I've missed something. Oh, and of course in Python, functions are defined by def instead of function. Now I'm not getting anything yet. First of all, because I haven't printed anything. Second of all, because this function isn't actually returning anything. So what I'll say is return effective FAR. So what that does is it returns the effective FAR calculated within this function out back to where we called it. So you can see that if our cutting height was, instead of 260, if it was 200, our effective FAR oh, whoops, the other last thing we need to do is we've passed in h. So actually instead of cutting height, this is h. I'm going to set this point back to 0, 0. So if we cut at 200, our effective FAR is 6. If we cut at 300, our effective FAR is 13, and so on and so forth. So this is very convenient. Now the next thing I'm going to do is I'm going to wrap this inside a loop. So for x range, so this is a loop. Whoops. Forgot that this is a function. Basically this means x range 5 gets you from 0 to 4, and it says, and this basically loops between 0 to 4 because x iterates on this list. If I say if you print range, you get 0 to 4. X range is basically similar to range, except that it doesn't store variables in memory, so it's more memory efficient, but you don't really need to know that. So for x in x range 5, print x does a loop 5 times. And if instead of x range 5, if we put this in, it'll calculate this 5 times. And notice that this is actually pretty quick. That's the other thing about Python is that even though you're doing the same calculations that you'd be doing in Grasshopper and Rhino, it's actually faster because you're not actually having to display it. It's all doing it in memory, nothing to do with a 3D display. So what we're going to do is then say, we're going to initially set this cutting height to this one. And we're going to say, okay, cut at this cutting height. So it initially cuts at 260. And we say effective FAR. So now we have the cutting effective FAR, and we'll print it. And just so that we know what we're doing, I'm going to make a kind of statement in text. So we cut at height this cutting height, and the effective FAR was, so print that. We cut at height 260, and the effective FAR was 10.46. Print, so we should cut at, we should really try to cut for the next time with FAR so max FAR minus effective FAR is how much more we can do. And let's say, okay, only do half, or let's say 3/4 of that. And then we'll add it to the FAR we just attempted, or we just got. So this is saying we should cut at height 260 and the effective FAR is 10.46. So we should try cutting at FAR 17.6. And I'm actually going to make this. Now later you can clean this up, but I'm of the opinion that when you program things like that, it's way better to be hyper clear than try to be efficient. So we should cut with FAR. And so the next round of FAR, or next cutting height, is defined by this FAR. Of course, then this cutting height equals try FAR times floor height. Okay, let's see what's going on. Now, I see. This is a problem because you can see that we're actually cutting at a lower height, 229, 221, 219. So that's actually not what we're doing, and actually I'm going to reformulate this a little bit. I'm going to say that when a round starts within this loop, we first define a cutting height, and we start out with a try FAR. Now the try FAR initially is going to be the same thing as a max FAR, because we're going to say, because we're creating these voids, we're going to say, well, let's start out with the height or the FAR of our initial volume, initial maximum volume. So try FAR equals max FAR initially. So initially try FAR is going to be 20. So this cutting height equals try FAR, which is 20 times floor height. Do all this stuff, we'll cut the height, and then this is how much more you should cut with, this number. So you need to add it to the try FAR, which is this. So we should, to try FAR, we should add this to itself. Another syntax for that in programming is to do plus equals. So try FAR equals try FAR plus this. So if I run this, I'm going to add another white space so that we get kind of more formatted output. So we're cutting at 219, and the effective FAR was 7. We cut at 341, so the effective FAR was 16. We cut at 379, the effective FAR is 19, 19.75, 19.93. So you can see that already it's converging. If I do this 10 times instead of 5 times and run it again, you can see that now at the end, the effective FAR is converging to 19.9999. So we've effectively created this thing that measures our height. So our cutting height is at 392.25, which is great. So that's pretty much done. The last thing is we can say final cutting height equals, by then you get this try FAR, which is this number, or try FAR, which is, if you want to compute the final cutting height, this number. So try FAR times floor height. And instead of using A, I'll call this final cutting height. And if I run this, our final cutting height is 392.25 feet. So we can do that to then actually give us a cut. But you know, we did this process already, and I think we might as well have it return the actual split mass to us as well. So there are a few ways to do this, but I'm just going to copy this. Or actually, one thing I could do is I could copy this entire function and paste it. Instead of this getting the FAR at height, I could say get lower mass at height. And when it does all the cutting, we'll say, well, don't worry about calculating the FAR, just return the split lower mass. And you can see that I've, named my variables pretty explicitly and descriptively. It's always a good thing. If you start naming these things, random variable names, you start to lose sight of what you're doing very quickly. So this returns the lower mass, so we can say, okay, great, the final cutting height is that, the final lower mass equals, get lower mass at height, final cutting height. I'm just going to press F5 to run it. Looks like it went off without a hitch. The last thing to do is make sure that Python exports final lower mass. And if I look at that geometry, I might have to middle click on this and click on the play button again to make it run. So I've created a closed brep as a result, which is very exciting. And so instead of previewing something else, I'm just going to preview this thing. I'm going to hide everything else. So this is super exciting. And so if I show my geometry again, you can notice that as I move the ball out, the height of the mass changes. Now it's a little slow, you'll notice, and you can see that it takes 554 milliseconds. If you don't see that, you could go into Display, go into Canvas Widgets, and click on Profiler, which shows you the time it's running. The reason why this is slow is because this is doing brep subtraction. I found that if you do meshes, it's oftentimes much faster. So now we have the subtraction, and arguably this has created a tool that the process of modeling involves creating these kind of negative forms and kind of selectively inserting them into this mass. The other thing I'm going to do is I'm going to do this one small trick that is actually really helpful, because here the question is, how do you see what the mass is? You're dealing with rhino geometry, but there's no way in Grasshopper to hide the rhino geometry. So instead of actually hiding the rhino geometry, I'm going to use a little trick with the Flounder components, which I don't actually hide any geometry, but I just move the camera over in a very different location, and move all the objects over so that when I'm previewing what's on the screen, I'm seeing all the Grasshopper geometry, but not the rhino geometry. Better explained by doing than saying. So I'm going to use these two components, which are two halves of a whole. I'm going to say synchronize the design viewport to the model viewport. I'll use the timer component to make sure that this computes every, say, 20 milliseconds. I'm going to turn this on. And if I just connect the location of the cameras together, they'll start to sync. But that's not actually what I'm going to do. What I'm going to do is I'm going to move this object in the x direction, doesn't really matter, in a very large distance. And I'm actually going to show this one instead. And I'm also going to move the cameras a very large distance. So the location is moved 1,000 units in the x direction. The target of the camera is moved 1,000 units in the x direction. And the lens is the same because the lens is a number, and so does everything else. And then I'm going to hide everything. And so essentially what's going on is these objects are in a different location in the x dimension. To clarify that, I'm going to set this to 50, or sorry, 200, maybe more like 1,000. And so if I zoom out, you can see that this geometry is just being moved over here. But if I just, but if I move it out far enough, it really doesn't matter where it is, then I just can't see it within my viewport. And if I just hide everything properly, and I make sure that I'm going to use the same vector for moving everything, then it will look like everything is synchronized, right? But instead of doing custom preview, I'm just showing this Grasshopper geometry in a different location. So you get the illusion of synchronicity, or the illusion of actively hiding Grasshopper geometry. So that way I can get my extruded geometry of my original envelope. So I'll do get my original envelope geometry. and I'll kind of just display it. And then eventually create this process in which, this process says, okay, well, given this lot line and given this geometry, I can create some sort of a massing by essentially crafting the negative objects in the space. And of course, I could use remote control panel and etc. But now, if you think about what exactly I've done in terms of the computational complexity, I've used Grasshopper and Python to calculate the max F error of this, but that's not, it's one value, that's just analyzed one number. It's a fact that I've incorporated into this interface that's more important than the specific analytical abilities of that tool. In other words, every metric is a tool, or every metric can turn into a tool. Now, this isn't automatically generated for me. This isn't, being smart. I don't want a smart tool. That's in some ways the opposite of what I want. I want a tool that, given certain properties, is able to restrain me from doing certain things. In this case, this is kind of a refusal. It refuses to, go up or down below a certain height. It refuses to extend beyond the lot line. Hopefully that was like a good kind of primer into how to use Python in creating this tool environment. Moving the geometry to a different location is actually a really powerful tool. And in one of the next tutorials coming up in the next class, which I'll call pinup table, I'll show an example of a tool that uses this to kind of array or bake a different series of results onto a surface so that you can kind of compare between different processes and different decisions.